Welcome everyone! Today, we are diving deep into the world of exploration geochemistry and uncovering the powerful statistical tools that turn raw data into multi-million-dollar discoveries. From the moment a sample is pulled from the ground, statistics are at work, ensuring every piece of information is reliable and ready for analysis. So grab your notebooks and let's explore the numbers behind finding the next big ore deposit. First things first, how do we know our data is any good? This is where quality assurance and quality control, or QA or QC, comes in. Think of it as the foundation of our entire project. Statistical methods are the backbone of QA or QC, helping us monitor three key things: precision, accuracy, and contamination. A solid QA or QC program gives us the confidence to trust our results and understand their limitations. Let's talk about precision, which is all about consistency. Are our measurements repeatable? To check this, we use duplicate samples, field duplicates taken right at the source, and pulp duplicates prepared in the lab. One common test is the percent relative standard deviation, which we use to evaluate these duplicates. Ideally, we want this to be 5% or less for major elements, and between 5 to 10% for most trace elements, though it can sometimes go higher for trickier metals. However, the gold standard for measuring precision is the average coefficient of variation. This method is incredibly robust because it doesn't care if your data follows a perfect bell curve or not. It works equally well for elements that have a nugget effect, where you might find a tiny, high-grade speck of gold that throws off your average. For duplicates taken in the field, we aim for this value to be less than 10%. For duplicates processed in the lab, we want it to be even tighter, under 5 to 7.5%. We also use visual tools like Thomson-Howarth plots and simple scatter plots to spot check our duplicate data. And to confirm that two sets of data are truly related, say, the original half of a drill core and its duplicate, we calculate the correlation coefficient, which gives us a numerical score of their relationship. Now, let's move on to accuracy. Accuracy measures how close our results are to the true certified value. We test this by sending known samples, called certified reference materials, to the lab along with our regular samples. We then calculate the percent relative difference to see how far off our lab's measurement was. For a more rigorous check, we can use statistical tests like the t-test, which compares our measured average to the certified average, taking into account the sample size and known standard deviation. Another powerful visual tool is the Shewhart control chart. This chart tracks our results over time. If a data point falls outside 3 standard deviations from the accepted mean, it's a red flag. This tells us it is time to investigate our sampling and lab procedures to find out what went wrong. Sometimes we need to compare entire sets of data, maybe from 2 different labs or 2 different sampling methods. To do this, we use statistical comparison tests like the F-value, paired t-tests, and pool t-tests. These help us check for equality and eliminate any systematic bias between the data sets, ensuring we're comparing apples to apples. Once we're confident in our data quality, it's time for the exciting part: exploratory data analysis, or EDA. This is our first real look at the story the data is telling. We start by analyzing the frequency distribution of a single element using tools like histograms and cumulative frequency plots. This helps us see the data's overall shape. Is it a normal bell curve, or is it skewed? Are there multiple distinct groups of data, which we call populations? And most importantly, are there any outliers, those extreme values that could signal something special? We also look at measures of central tendency. The mode, or the most frequent value, often represents the normal background concentration of an element. The median is the middle value, and the mean is the simple average. However, the mean can be easily skewed by a few unusually high values, so we have to be careful with it. A key goal here is to determine the threshold value. This is the statistical line in the sand that separates normal background values from potentially significant anomalies. Any sample that pops above this threshold is worth a closer look. Because many elements in nature follow what's called a log-normal distribution, we often need to transform our data. A common technique is the log transformation. By taking the logarithm of our data, we can often make a skewed dataset look more like a normal distribution. This allows us to use a wider range of standard statistical tests. We can quickly check if this worked using a normal probability plot. For skewed data, another useful method is the median absolute deviation, or MAD. Instead of using the mean, we set our threshold at 2 median absolute deviations from the median. This approach is great because it minimizes the influence of those extreme outliers. We also use visual tools like quantile plots and box plots to get a deeper understanding of our data's distribution and characteristics, but exploration geochemistry is rarely about just one element. Or deposits are complex, and anomalies often show up in multiple elements at once. This is where multivariate statistical analysis comes in. It helps us understand the associations between different elements. A simple starting point is the correlation coefficient matrix, which quickly shows us which elements tend to appear together. Building on this, we use cluster analysis to group elements that are highly correlated with each other, separating them from other groups. A powerhouse technique in multivariate analysis is principal component analysis, or PCA. PCA takes all our variables and creates new uncorrelated variables called principal components. Each principal component is a linear combination of the original elements. The beauty of PCA is that it often allows us to reduce the complexity of our data. We can focus on just the first few principal components that explain most of the variability, making our dataset much easier to interpret. Sometimes we even rotate these components to make them align more clearly with the original data. Another powerful technique is factor analysis. This helps us extract the main geochemical factor or signature associated with a specific type of mineralization. For example, we could create a gold factor map that highlights areas with the right combination of elements that typically accompany gold. To refine this, we might use a staged factor analysis, where we iteratively run the analysis and remove elements with weak associations. This helps us zero in on a reliable, multi-element signature for our target mineralization. And what about multivariate outliers? We can detect these using something called Mahalanobis distance. This measurement considers the means, variances, and relationships of all the variables at once. Samples with a large Mahalanobis distance are flagged as outliers, which could be data errors or, more excitingly, genuine anomalies. We also have to remember that geochemical data is often compositional. This means the components add up to a constant, like 100% or 1 million parts per million. Standard statistics can get tricky here. So we use a special approach called compositional data analysis, or CODA. The key is to use log ratios, the logarithm of the ratio between different components. This transformation frees the data from the constant sum constraint. A common method is the centered log ratio transformation, which normalizes the data. Once transformed, we can apply all our usual univariate and multivariate statistical methods without any issues. Now let's step into the third dimension, space. Geostatistics is a branch of statistics that incorporates spatial relationships into the analysis. It's what allows us to build 3D models of all bodies and estimate resources. The foundational tool of geostatistics is the variogram or semivariogram. This incredible tool helps us model the spatial complexity of a deposit. It quantifies how similar samples are to each other based on the distance and direction between them. The variogram is crucial for everything from designing optimal drilling patterns to estimating resources. The most famous geostatistical technique is kriging. Kriging provides the best linear unbiased estimation of values at locations where we haven't sampled. It uses the spatial structure defined by the variogram to intelligently weigh the influence of nearby samples. But what about uncertainty? Geostatistical simulation, like sequential Gaussian simulation, addresses this. Instead of creating one single best guess model, simulation generates hundreds of possible models, all of which honor our data and the variogram. This collection of models gives us a powerful picture of the uncertainty in our grade estimates, which is critical for making risk-informed decisions. The estimation variance, calculated from the variogram, numerically quantifies this uncertainty and helps us decide if we need more drill holes to be confident in our resource model. Moving to the cutting edge, we have predictive modeling and multi-criteria decision-making. These methods integrate our geochemical data with geology and geophysics to create mineral prospectivity maps that highlight the most promising targets for future exploration. One fascinating approach is fractal modeling. Fractal models, like the concentration number and concentration area methods, are excellent for classifying our evidence layers and pinpointing highly favorable zones. A huge advantage is that they don't require all the PRE processing that other methods do. To combine all these different data layers, we use outranking methods like TOPSIS and VCOR. These techniques weigh each layer of evidence based on its importance, which we often determine using expert opinion through the Delphi method. We can then perform a sensitivity analysis by leaving one layer out at a time to see how much it affects the final prospectivity map. This tells us which data layers are the most critical for finding our target. Finally, there's a fascinating mathematical model called Zipf's law. By ranking the metal content of known deposits in a region and plotting them, we can sometimes identify missing links in the pattern, pointing to the potential size and location of undiscovered deposits. Of course, there are also many other valuable estimation and visualization methods we use every day. Isograde contour maps give us a 2D picture of how element values are distributed, guiding our next steps. Inverse power of distance is a straightforward interpolation method for estimating grades. Bivariate scatter plots, triangular diagrams, and 3D plots are fantastic for visually inspecting our data and spotting unusual multi-element signatures. And when we calculate the average grade of a drill intersection, we use statistics to define a confidence limit around that average. Probability and frequency models even allow us to track how our precision improves as we increase our drilling density, helping us manage exploration projects efficiently. As you can see, statistics are absolutely essential in modern mineral exploration. They guide us every step of the way, from ensuring data quality to building complex resource models and predicting where to find the next major discovery. It's a fascinating blend of geology, chemistry, and mathematics that drives the mining industry forward. Thanks for joining me on this deep dive. I hope you found it insightful. If you enjoyed this video, please give it a thumbs up and don't forget to subscribe for more content on the science of exploration. See you next time.